back to a new episode of Passion for Technology, the podcast from EPD Electronic. Great to have you with us.
Welcome to the Passion for Technology podcast. There are two key reasons why the number of analog ICs keeps growing. There is an increased use of sensors and an increased need for power management solutions. A 2020 study by the Wilson Research Group concluded that returns of analog components in the field had also increased. This seems to indicate that the design of analog ICs and their integration into solutions is complex and requires specialist know-how. We'll be discussing why that is the case and how the semiconductor industry is supporting electronics designers working with analog ICs. I'm joined by two guests today. Alessandro Zaffarana, power technologist at onsemi. Hi, Alessandro.
Hello.
And Andreas Genzer, Senior Product Marketing Manager at Infineon. Hi, Andreas.
Hi, thanks for having me.
Thank you both for being here. Andreas, how would you explain the results of the 2020 Wilson Research Group study? Why is the design of analog ICs so different from the design of digital ICs?
So I think when reading the study, there is two aspects that I would say are very important to mention. The first one potentially states a bit the obvious because we are all living in a time where we have an ever-increasing number of transistors that gets integrated on a single IC design. So if we go back, I think it's almost 50 years now when Mr. Moore defined Moore's law, saying the number of transistors doubles around every 2 years. So what we simply get much more computational power on our ICs. And I think this is what the Wilson study shows very well because it shows that the high gate complexity designs are in a majority. One aspect maybe that is very interesting to mention here, and it also has an impact on IC design, especially analog design, is potentially artificial intelligence. Because artificial intelligence is also a driver and requires those high-performing, high-gate complexity designs. What I found quite interesting, because I recently read an article where it was compared how artificial intelligence is changing our world, right, and what it is capable to do. And the comparison was about chess. It was about the Chinese game Go. And it was, coming back to analog design, about how to place components on an IC in a smart way during the floor planning process. And I found the results very interesting. Because if you look at chess, AI bet the best chess player in 1996 already. So this is 25 years ago. And high-performing computer and artificial intelligence was capable to beat a human player back then. It took almost 20 more years. I think it was in 2015 when Google's AlphaGo was beating the best human Go player, which simply shows, right, we have so much more processing power in our IC designs. We have so many advances in AI in the meantime, but it took 20 more years. And finally, the comparison to how AI can assist IC design in floor planning, as I mentioned before, this is an order of magnitude, a mind-blowing amount of orders of magnitude more complex than beating a human player in Go. So I think that's also a very interesting outcome in terms of how much more we need these high gate complexity designs in order to power use cases like the one I mentioned. The other aspect, and that's the second aspect, and that's the perhaps more surprising fact the study reveals, is that we also see quite some low complexity designs increasing. And this to me points a lot into analog content, into analog ICs. And that's potentially, for example, could be sensor nodes that are deployed somewhere out there in order to sense air quality of Paris, for example. And you see, I'm pointing already towards use cases that I associate with IoT, the Internet of Things. Because these sensor nodes, Internet of Things objects, are becoming ubiquitous. They are penetrating our everyday life. And I would interpret the study result in that way that also the analog part, the low complexity gate count, is increasing because IoT, which demands analog content, is a big driver here.
Alessandro, how can the design complexity be reduced?
The complexity of the design, anytime that we cope, of course, with analog and power and eventually also digital, because in reality, to be clear, analog design sometimes needs to be mixed with the digital. because analog is referred to the sensor, and our world, of course, is made by sensor. I would say that in reality, our world is analog because we are surrounded by sensors, I would say. Sensors at the end must also be handled and converted into digital in order to have a flexibility and in order to also build interfaces, digital interfaces with other domain. So the complexity is referred to the mix between analog and digital. And the complexity from semiconductor design perspective can be, managed in terms of risk of design, in terms of reutilization of the main building blocks of the system, in terms of course, EDA tools, and of course, even the manufacturing process can help to make the designer life easier.
Integrating analog, power, and digital ICs in a system on a chip becomes increasingly difficult as digital components are shrinking at a faster rate than what's possible for analog ones. What solutions is the semiconductor industry offering, Andreas?
Very good point. It's indeed a challenge. And how I see it, combining analog and digital essentially means doing the following. And let me maybe put it a little bit to the extremes. You're trying to combine a relatively cheap technology, that's more the analog portion, with a relatively expensive technology. If we, for example, take 7 nanometer technology, where today high-performance system on chips are built that are running in our mobile phones, right? And combining these extreme cases is not necessarily the sweet spot in terms of cost and being competitive out there, right? So I think what's very important for our semiconductor vendors to do here, we need to know our markets. So we need to know our markets, see what's really necessary when it's coming to integrating analog and digital and getting into the sweet spot in order to be cost effective. So I think that's very important. Let me maybe give you an example. A microcontroller today is a very good example of integrating both digital and analog, because the microcontroller by itself, I would consider it as a digital device. But then you have analog to digital controllers on there in order to get analog input from the outside world. And that's an analog component. And this integration is state of the art today. This is something obviously the industry is willing to pay for and what customers value. But then there is other examples where it's better to be standalone and have analog components on a PCB and have digital content somewhere else. This sweet spot technology is a very important point that we all should keep in mind.
I fully agree with what Andreas reported, but I will also add a few other things about the integration between analog and power. I was just referring previously that at the end, the analog devices will be a tool to provide more value to the customers, in particular when the analog is embedded together with the digital. So the example that Andreas was reporting about the microcontroller is absolutely very effective to emphasize this merge. I will also add here that the analog integration is an artistic, I would say, activity. While the digital design somehow has similarities with the coding at the end, so it is also pretty straightforward for a digital designing, having in mind, a factorization that is typical of the software design. Analog is made by analog portions that will also interact together. And there is a creativity behind the analog that comes from the experience of the analog designers. In fact, it is very well known that today in the manpower hiring activities, analog designers are maybe the most paid, I would say, designers, because their experience can really provide an added value in this integrating activity between analog power and digital. And another comment that I have about the integrating is that the semiconductor industry today is now shaped around this integration. For instance, an example is related to the BCD technology. BCD technology is now very common in the industry. There are several foundries that provide BCD technologies where bipolar, CMOS, and digital are merged together in order to provide the chance to have really an added value for the semiconductor company, offered into the market.
Increased power efficiency, system reliability, and safety are ultimate trends. How does this reflect on smart power management, Andreas?
It's a big question. First of all, I agree. These are key trends we see across many industries that we as semiconductor vendors operate in. So let me give you maybe one example. If I think about industrial robotics, first of all, power efficiency is key there, which we enable with, for example, wide bandgap devices today. The other thing is reliability, which, I mean, if I think about industrial robot, ideally, there is an uptime of 24/7, 365. At least we should be very close to that. And the other topic is safety. I mean, if you think about those robots were kept away to get in touch with humans, but within industrial robotics, today you have a big trend, which is collaborative robotics, where humans work together, they can potentially touch the robot. So I think safety, reliability, and power efficiency, I think they're where they come to play. Let's say, I think where we as semiconductor companies can contribute there also in terms of smart power management, let me maybe add two aspects. One is related to reliability, one is related to safety. And this is isolation and protection. So if we just imagine for a second a power electronic system, usually you have the low voltage portion where your microcontroller sits, where a human can even touch a human machine interface like a display. On the other hand, you have the high voltage side where you can have hundreds of volts. And if something is going wrong there, you need to make sure that humans don't receive any harm. And this is where isolation comes into the game. And the very natural component between the logic side and the high power side is the gate driver. And it's pretty standard out there that gate drivers implement this isolation and they do it in a safe way. We from Infineon, we are providing such components that then go well together and keep the safety aspect in the system. Sorry for my long answer. Let me just add one more word on the protection side. Protection circuitry is also a very important point because coming back to reliability, if there is a failure in your system and your system gets damaged, you have a downtime. This is not what you want in an industrial automation setting. So protection circuitry is very important. And if you again look into power electronics, we have power switches out there. If they are going into short circuit, you need to be very fast to detect this short circuit and turn the system off. And again, there we as an industry, we are providing components, the gate driver, the power switch in combination, which are actually accomplishing that. So I think these are just two examples how we as vendors contribute in order to help in these ultimate trends.
Alessandro, what role does packaging play in the design of analog and power ICs? I mean, especially in terms of space, performance, and energy efficiency.
Wow, and packaging is an essential ingredient for a good cake, I will say. Well, the cake can be also digital indeed, but in analog, the packaging is absolutely a relevant ingredient because in reality, anytime that the analog function is needed at the system level, this happens because at the end, the final customer is really keen on having the best performance because the analog, of course, doesn't have, for instance, the latency that the digital may have. And anytime that the customers must interact with the sensor, the analog is essential. So I would say that the power efficiency is, of course, another important ingredient of the analog design because of this reason. And the packaging is a complementary to the power efficiency ingredient. Packaging is also responsible for the power efficiency. Interconnections, parasitic inductance, stray capacitance among the pins of the device are all basically essential requirements, very important parameters of the analog integration into the system. Packaging today represents also the chance to add more values beyond the analog function per se. Packaging today may even embed passives like capacitors or eventually RF filters. Talking about the power efficiency, packaging will permit to embed important capacitors, for instance, the booster capacitor of a driver, so improving also the switching losses of a power driver. So packaging is extremely important. And without the packaging, I will say that advanced analog will not have the same value.
Maybe let me add to Alessandro, because I completely agree. And maybe just let me add another example why packaging is so important. And I think sometimes it's not fair, right? If you look at products that we provide, usually that the features that customers see, let's call it the fancy features, you won't find packaging in there. It's in the end not fair. And let me just add one thought I have here. Again, coming back to power efficiency, right? So we are in the midst of a trend where we are going towards wide bandgap technologies like silicon carbide. What we do is we increase switching frequencies there. This is good because we make systems more power efficient. But even though now a package of an IC is a very small component, package parasitics become more important if you increase switching frequencies. So it simply raises the bar in order to do a successful product. The other thing is mechanical stress, right? So, I mean, if you stress a package mechanically during lifetime in a system, this can have an impact on the circuits in the package. So perhaps reference voltages change over lifetime. There is many aspects like this that raise the bar nowadays on the packaging side, which can have an impact to do successful products overall. So I think we should never underestimate how big the role of successful packages is in order to do successful products.
Absolutely true. I would even add, because the packaging feature is also very close to my experience right now in onsemi, that basically how much is important the package here is also related, to the material and to the assembly techniques. Of course, advanced research into thermal conductivity, into reduction of the parasitics, like, of course, removing, for instance, the bonding wires, replacing with the flip chip techniques combined with the copper pillars. All those things, of course, are very important to really provide a good solution to the final customer.
Shifting our focus a little to power conversion, Andreas, is power control going fully digital, or are there any advantages to analog components?
Let me put it that way. There's definitely a trend towards digital, and this, I think, comes simply from a number of advantages that digital offers. And let me maybe come back to my initial words on Moore's law. I mean, what is a fact is that every new year we have more computational power on a microcontroller where potentially our control algorithm runs, right? So in other words, you can run something much more sophisticated in terms of digital or in terms of control than you could a few years back. Or put differently, you can simply run an algorithm that you developed 5 years ago. You can simply run it on a much cheaper device. This would speak for digital control, right? Another one is maybe flexibility. Just imagine if you have an analog control, if you want to change it, you need to change your PCB. In a digital controller, you change software. That's much easier. If you need to debug, you need to do PCB iterations in the analog world. In the digital world, you do software debugging. So this is what all speaks for digital, right? But I quite believe that analog control will be with us longer than many would expect. And this comes again back to our initial discussion with IoT, in my opinion. Because IoT means you have sensor systems out there deployed, and these systems have a very limited energy budget because you don't want to change batteries every few months. Ideally, they last 10 years. So these are ultra low power systems. What you won't have on this system is a highly capable system on chip or microcontroller that can run fancy digital control algorithms. You might think about doing this in analog because you can do analog control very, very power and energy efficient. So that's why I think that, yes, there might be a trend to digital, and what can be done will be done in digital. But because of trends like IoT and very power and energy constrained systems, analog control will be there for a very long time.
Alessandro, how is the semiconductor industry helping designers with utilizing analog components?
Yeah, I mean, this is also a very good question that would open a chapter. It is quite long. Indeed, before to proceed with the answer to this question, I would even comment more about the previous questions that Andreas answered. I mean, is power control going digital or analog? So I would say that we should avoid the classic dichotomy between, I would say, digital and analog. Of course, power is nothing without control. And there are basically sometimes products where the digital can really provide, the last mile in terms of flexibility, in terms of response optimization because of non-linearities, for instance. But there are some other products where absolutely the KPI are in analog domain. For instance, low latency, very high speed, low power consumption like IoT, where Andreas said. So is power control going digital or analog? I will say that it depends in reality. And then, going back to your questions about how the semiconductor industry can help designers. I mean, for sure, EDA tools recently have provided, new awesome, I would say, weapons in the designers' activities. And now they have optimization tools. Maybe in the future, they can also use some AI algorithms to extend, to stretch the usage of the basic blocks. And of course, BCD and advanced technologies combining digital and analog can also improve the designer's workout, I would say.
Alessandro, what technology trends are there that will make the design of ICs easier in the future? I mean, could AI be used to help designers with their challenges in the future?
Well, we have already seen that analog means a complexity, and the complexity of analog, as also we mentioned previously, depends on the fact that analog components will also interact among them. These interactions are multiple. They can be part of the design, but can also be hidden, I would say, inside the manufacturing process. So deep knowledge of the manufacturing process parameters are also mandatory, I would say, to prevent interactions that can create eventually issues. Also, environmental conditions can also influence the analog circuits, much more than the digital, I would say, the digital circuit. So this is the real complexity. AI can also help the designer to cope and to handle such complexity, because AI can receive the specification of the blocks, can prevent eventually issues that will come from such interconnection, and can suggest to the designers how to move parameters to reduce the influence of such issues. Artificial intelligence can also help eventually the designers to stretch out eventually the specification of each block, eventually helping the designers to extend the usage of a particular IC also to other features. And AI can also improve, I would say, the KPI of the product, trying also to extend the possible usage to other markets eventually. So AI will be definitely a part of the game, exactly combined, of course, with the experience of the analog designers that we have seen previously. There is also some artistic touch, I would say, behind the analog design.
Beautiful and deep insights. I very much enjoyed this, and it has become a little bit of a tradition that before we close our podcast, we ask our guests where and how you developed your respective passions for technology. Andreas, I'll start with you. How and when did you develop your individual passion for technology?
Well, I think it started very early in my life. So I think because the last 20 to 30 years, there was so much going on. And I think technology has penetrated so much of our everyday life. I mean, if I just think today, talked about IoT, if you think about blockchain development, so it's not just a niche thing anymore. It becomes really widespread. And I think I was always interested in these things. And since it can change so much in our society, hopefully for the good, I think this is where my passion for technology is coming from.
Alessandro, what about you?
Wow. It was clear in my life when I was a kid, starting playing with the Lego bricks at the beginning, and then also having the clear understanding that I really love to do things that can also help the life of the other people. So technology is an important tool of our life and also of our kids' life for the future, So my passion comes, from early age, I would say.
Dear listeners, if you'd like to get in touch with our very passionate and obviously very knowledgeable guests, feel free to reach out to Alessandro or Andreas on LinkedIn. So Alessandro is Alessandro Zaffarana on LinkedIn and Andreas is Andreas Genza. You'll be able to look up their last names and the exact spelling in our show notes. Please feel free to subscribe to our podcast, Passion for Technology, on either Spotify, Apple Podcasts, or any of the other popular podcasting platforms. Andreas, Alessandro, thanks once more for you joining and sharing your insights with us.
Thank you. It was fun.
Thank you. You're welcome. Goodbye.